Somewhere on the Giza Plateau, cut into the bedrock of a desert that has swallowed entire civilizations, sits a structure whose precision should not exist. The Great Pyramid of Khufu contains approximately 2.3 million stone blocks. Its base is level to within 2.1 centimeters across an area of more than 5.3 hectares. Its four corners form angles that deviate from a perfect right angle by an average of less than 3.5 minutes of arc. Its sides are aligned to true north, with an error so small that modern surveyors require laser instruments to detect it. And it was built more than 4,500 years ago, in an era when the most advanced cutting tool available was copper, a metal so soft it bends under hand pressure. Think about that for a moment. Copper cannot cut granite, and yet the Great Pyramid contains granite beams in its internal chambers that weigh up to 80 metric tons, quarried from Aswan, more than 800 kilometers to the south, and fitted together with joints so tight that a sheet of paper cannot be inserted between them. The sarcophagus in the king's chamber was hollowed from a single block of Aswan granite, using techniques that, according to modern analysis, achieved cutting rates consistent with the use of fixed-point diamond-tipped drills, a technology the ancient Egyptians are not supposed to have possessed. The drill holes found in granite cores excavated near the Giza Plateau show spiral grooves that advance at a rate of approximately 2.5 millimeters per revolution, a feed rate that the engineer Christopher Dunn has argued exceeds what can be achieved by hand with any known ancient tool. Something does not add up. The orthodox explanation for the construction of the Great Pyramid involves copper chisels, wooden sledges, ramps of packed earth, and an enormous labor force working for approximately 20 years. This explanation is not wrong, but it is incomplete. It accounts for the general scale of the project, but not for the precision. It explains how millions of blocks could have been moved, but not how they were cut and placed with such extraordinary accuracy. It tells us that the pyramid was built, but not how the builders achieved tolerances that rival modern engineering. And the gap between what we can explain and what the evidence demands is where the real mystery begins. We are told that the ancient Egyptians built the Great Pyramid with copper tools and human muscle. We are told that thousands of workers hauled stone blocks across the desert on wooden sledges, dragging them up earthen ramps to their final positions. We are told that the project took approximately 20 years and employed a rotating labor force of perhaps 20,000 to 30,000 workers. This narrative is not fabricated. It is supported by real evidence, including the Wadi al-Jarf papyri, the workers' village discovered at Giza, and the quarry marks found on pyramid blocks. But it is also incomplete. It is like describing a symphony by listing the instruments used. Technically accurate, entirely insufficient. There is a particular kind of lost knowledge that haunts the Great Pyramid. It is not the knowledge of how to organize a labor force. We understand that reasonably well, thanks to recent archaeological discoveries. It is not the knowledge of how to quarry limestone, which is relatively soft and can be cut with copper tools. It is the knowledge of precision, the knowledge of how to achieve alignment to within fractions of a degree, the knowledge of how to level a surface of more than 50,000 square meters to within centimeters, the knowledge of how to cut and fit granite with tolerances measured in thousandths of an inch. This knowledge existed. The physical evidence proves it existed, and it has been lost so completely that we cannot reconstruct it with certainty, despite more than 2 centuries of sustained effort by some of the finest minds in archaeology, engineering, and materials science. The Great Pyramid is not merely an ancient monument. It is a technical document written in stone. Every measurement, every angle, every joint is a piece of data about the capabilities of the civilization that built it. And when we read that data carefully, when we measure what the pyramid actually is, rather than what we assume it should be, the picture that emerges is one of a society that possessed engineering knowledge far more sophisticated than the standard narrative of ancient Egypt allows. Not magic, not alien technology, not fantasy, but real, practical, hard-won knowledge of materials, geometry, astronomy, and construction management that was developed over centuries, and then, after the Pyramid Age ended, was gradually, irreversibly lost. By the end of tonight, you're going to understand what that knowledge was. You are going to see, through measurements and evidence, and the painstaking work of researchers who have spent their careers studying this single structure, exactly what the builders of the Great Pyramid knew. You are going to learn how they achieved what they achieved, and you are going to confront the uncomfortable truth that much of what they knew we still do not fully understand. Not because the knowledge is beyond human capacity, but because the chain of transmission that carried it from one generation to the next was broken. And once broken, some knowledge can only be recovered through the agonizing process of working backward from the evidence it left behind. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. To understand what was lost, we first need to understand what was built. And to understand what was built, we need to begin with numbers. Not approximate numbers, not rounded off, impressive sounding numbers, precise numbers, because it is in the precision that the mystery lives. The Great Pyramid's base measures approximately 230.34 meters on each side. The variation between the longest and shortest sides is less than 20 centimeters across a total perimeter of more than 920 meters. That is a deviation of less than 0.02%. To put that in perspective, consider that a modern construction project of equivalent scale, using laser-guided surveying equipment and GPS positioning, would typically aim for a tolerance of plus or minus 5 centimeters over a comparable distance. The builders of the Great Pyramid, working with whatever tools they had, achieved a tolerance that is within the range of modern construction standards. They did this more than 4.5 millennia ago. They did it on bedrock. They did it once, as far as we know, without the benefit of a test run at full scale. The leveling of the base is equally extraordinary. The Giza Plateau is not flat. It is natural bedrock that slopes and undulates. The pyramid builders did not simply find a flat surface and build on it. They created a flat surface. They leveled the bedrock, in some areas cutting away rock and in others filling depressions, to produce a platform that is level to within 2.1 centimeters across the entire base. That is an area of approximately 53,000 square meters, leveled to within a tolerance that most modern residential contractors would consider exceptional for a house foundation. The standard explanation for how this was achieved involves cutting channels into the bedrock, filling them with water, and using the water surface as a reference plane. This method works in principle, but achieving the documented accuracy with this method over an area of more than 5 hectares requires a level of care, skill, and systematic quality control that is itself remarkable. The question of how the builders achieved their extraordinary leveling accuracy opens a window into the methodological knowledge that has been lost. The water channel theory, often cited as the standard explanation, proposes that trenches were cut into the bedrock, filled with water, and the water surface used as a level reference. Marks were made at the waterline, the water was drained, and the rock between the marks was cut down to the level of the marks. This method is logical and could work in principle, but it faces practical challenges that are rarely discussed. Water does not maintain a perfectly level surface when distributed across a large area in open channels. Wind, temperature gradients, and the capillary effects of rough stone surfaces all introduce disturbances. The channels themselves would need to be interconnected to ensure a consistent water level, and any blockage or irregularity in the channels would compromise the accuracy of the system. To achieve the documented accuracy of 2.1 centimeters across an area of more than 5 hectares, the water channel method would require extraordinarily careful implementation, with quality checks at multiple stages and corrections for any detected deviation. An alternative theory, proposed by the French surveyor Claude Crozier, suggests that the builders may have used a system of plumb bobs and sighting rods to transfer a level reference across the site. This method, which is well documented in later Egyptian surveying practice, involves sighting horizontally from a known reference point to a distant rod and marking the point where the line of sight intersects the rod. By repeating this process across the site, a level plane can be established with high accuracy. The advantage of this method over the water channel method is that it does not require the construction of an extensive network of trenches and is less susceptible to the disturbances that affect water surfaces. But whichever method was used, the result is the same: a surface of more than 50,000 square meters leveled to within centimeters. This is not a skill that can be improvised. It requires training, practice, and a systematic methodology that ensures consistent quality across the entire site. The knowledge of how to do this, not as a one-time feat of genius, but as a routine construction operation, is one of the specific capabilities that was lost when the pyramid building tradition ended. The internal structure of the Great Pyramid reveals another dimension of the builder's knowledge. The pyramid is not a solid mass of stone. It contains a complex system of passages, chambers, shafts, and voids that have been the subject of intense study and debate for centuries. The most recently discovered void, detected in 2017 by the Scan Pyramids project using muon tomography, a technique that uses cosmic ray muons to image the interior of large structures, is located above the Grand Gallery and measures at least 30 meters in length. Its purpose is unknown. Its existence was unsuspected before the muon survey. This discovery, announced by the physicist Kunihiro Morishima and colleagues in the journal Nature, demonstrated that the Great Pyramid still contains secrets that modern technology is only beginning to reveal. The Scan Pyramids discovery is significant, not only for what it found, but for what it implies about the limits of our knowledge. If a void of 30 meters in length could remain undetected inside the most studied structure in the world for more than 4,500 years, what else might be hidden within the pyramid's mass? What other features, passages, chambers, or structural elements might exist that our instruments have not yet detected? The pyramid was built by people who clearly understood the principles of concealment. The entrance to the descending passage was hidden behind a casing stone that was indistinguishable from its neighbours. The entrance to the ascending passage was concealed by a granite plug. The relieving chambers above the king's chamber were sealed and invisible from the accessible interior spaces. The builders clearly intended parts of the structure to remain hidden, and some of those hidden features may contain evidence that would shed light on the construction methods themselves. The mortar used in the Great Pyramid has been a subject of study in its own right. Analysis has shown that the mortar is a gypsum-based material produced by heating gypsum rock to drive off the water of crystallization, then grinding the resulting powder and mixing it with water and sand to form a paste. This process requires temperatures of approximately 130 degrees Celsius, which can be achieved in simple kilns. The quantity of mortar used in the Great Pyramid is enormous. Estimates suggest that approximately 500,000 metric tons of mortar were used in the construction. Producing this quantity of mortar required a massive industrial operation involving quarrying, kiln firing, grinding, and mixing on a scale that dwarfed any previous construction effort. The mortar was not used to bond the blocks together. As Petrie observed, the mortar was too thin in the joints to serve a structural purpose. It functioned as a lubricant, allowing the heavy blocks to be slid into position against each other with minimal friction. This technique, which is not intuitive and could only have been developed through extensive experimentation, demonstrates a sophisticated understanding of friction and lubrication that goes beyond simple construction practice. The builders had learned, through trial and error, or through deliberate experimentation, that a thin layer of wet gypsum mortar reduced the friction between stone surfaces enough to allow precise positioning of blocks weighing several tons. This is applied tribology, the science of friction, lubrication, and wear, practiced thousands of years before the science was formally developed. The alignment to the cardinal directions is perhaps the most discussed aspect of the pyramid's precision, and it deserves careful examination. The four sides of the Great Pyramid are oriented to the four compass points with an average error of approximately 3 minutes and 33 seconds of arc. A minute of arc is 1/60th of a degree. A second of arc is 1/60th of a minute. So the error is approximately 3.5 minutes, or roughly 1/17th of a degree. This is extraordinarily precise. It means that whoever laid out the base of the pyramid had a method for determining true north that was accurate to within a fraction of a degree. How was this done? Several methods have been proposed. The most commonly cited involves the observation of circumpolar stars, stars that are close enough to the celestial pole that they never set below the horizon. By observing the point at which such a star reaches its highest position in the sky, and the point at which it reaches its lowest, and then bisecting the angle between the two positions, an observer can determine the direction of true north with considerable accuracy. The Egyptologist Kate Spence of the University of Cambridge proposed in 2000 that the builders used the simultaneous alignment of two specific stars, Kochab in Ursa Minor and Mizar in Ursa Major, which would have formed a vertical line passing through the celestial pole at around 2480 before the Common Era, close to the estimated date of the pyramid's construction. Spence's theory is elegant and mathematically sound, and it has the advantage of explaining not only the accuracy of the Great Pyramid's alignment, but also the slightly larger alignment errors found in pyramids built earlier and later, when the two stars would not have been as precisely positioned relative to the pole. But the method, whatever it was, required more than astronomical observation. It required the ability to transfer an astronomical sighting from a small reference point to a building site covering more than 5 hectares. It required the ability to maintain that alignment across hundreds of meters of construction. It required a surveying methodology that could translate a celestial observation into a terrestrial layout with extraordinary fidelity. The astronomy is only half the problem. The other half is the engineering of the survey itself. The cubit, the standard unit of measurement used in Egyptian construction, deserves attention as an artifact of the knowledge system that built the pyramids. The royal cubit measured approximately 52.4 centimeters and was divided into 7 palms, each palm further divided into 4 fingers, giving 28 divisions in total. Cubit rods, physical rulers marked with these divisions, have been found at multiple Egyptian sites and demonstrate a standardization of measurement that was maintained across centuries. The precision of these rods is remarkable. Surviving examples show variations of less than 1 millimeter from the standard length, indicating a system of quality control in the production of measuring instruments that was itself a form of technical knowledge. The cubit was not merely a unit of length. It was the basis of a comprehensive measurement system that extended to area, volume, and slope. The sect, the Egyptian measure of slope mentioned in the Rhine Papyrus, was defined as the horizontal displacement in palms per cubit of vertical rise. The slope of the Great Pyramid, approximately 5.5 palms per cubit, corresponds to an angle of approximately 51 degrees and 52 minutes. This system of measurement allowed the builders to specify and verify the slope of the pyramid's faces using simple measuring instruments, a cubit rod and a plumb line, without needing to measure angles directly. The standardization of the cubit across Egyptian society was maintained through the production and distribution of official cubit rods. These rods were calibrated against a master standard and distributed to construction sites, administrative offices, and temples. The maintenance of this standard required an institutional commitment to measurement accuracy that is itself a form of knowledge. The knowledge of why standardization matters, of how to produce and verify calibrated measuring instruments, of how to distribute them and ensure their use, is organizational knowledge of a high order. It is the kind of knowledge that makes precision construction possible, not as an exceptional feat of craftsmanship, but as a routine operation. The surveying knowledge of the ancient Egyptians is one of the least understood and most important aspects of their technical capability. We know from textual evidence that the Egyptians practiced a profession they called stretching the cord, a ritual associated with the foundation of temples and other important structures. The ritual involved the pharaoh and a priestess of the goddess Seshat, the patron deity of writing and measurement, stretching a cord between stakes to establish the alignment of the building. This ritual is depicted in temple reliefs from various periods and is clearly more than a ceremonial formality. It represents a real technical process, the laying out of a building according to astronomical alignments. But the details of how the process was carried out, what instruments were used, what techniques were employed to ensure accuracy, are not described in any surviving text. This is a critical gap in our knowledge. The Egyptians were capable of surveying to extraordinary precision. The evidence for this is literally carved in stone, in the alignment and leveling of the Great Pyramid. But the methods they used to achieve this precision are not recorded, at least not in any document we have found. We are left to infer the methods from the results, like a detective reconstructing a crime from the evidence at the scene, without any witnesses or confessions. Sir William Matthew Flinders Petrie, often called the father of modern Egyptology, was the first person to survey the Great Pyramid with the precision necessary to reveal the full extent of its accuracy. In 1880 and 1881, Petrie spent months at Giza, meticulously measuring every accessible dimension of the pyramid and its surroundings. His published results, The Pyramids and Temples of Giza, released in 1883, remain one of the foundational documents of pyramid studies. Petrie's measurements were astonishingly detailed. He measured the base lengths, the angles, the heights, the dimensions of the internal passages and chambers, and the positions of individual stones, all with instruments that he had designed and calibrated himself. His work revealed for the first time the extraordinary precision of the pyramid's construction and set the standard for all subsequent surveys. Petrie was a careful, methodical scientist, and he was deeply troubled by what his measurements showed. The precision of the Great Pyramid's construction implied engineering capabilities that he could not easily reconcile with what was known about ancient Egyptian technology. He noted the extraordinary accuracy of the base leveling, the alignment, and the internal construction. He examined the granite work in the king's chamber and found that the surfaces had been finished to tolerances that he estimated at less than 1/100th of an inch over areas of several square meters. He found that the joints between the casing stones of the exterior, the fine white Tura limestone blocks that originally covered the pyramid's surface, were fitted so precisely that he could not insert a thin blade between them. The mortar used in these joints was not structural. It was, in Petrie's assessment, used as a lubricant to slide the blocks into position rather than as an adhesive to hold them together. The precision of the fit was sufficient to make mortar unnecessary. These observations raised questions that have never been fully answered. How do you achieve flat surfaces accurate to 1/100th of an inch over areas of several square meters using hand tools? How do you fit blocks weighing several tons together with joints so tight that no blade can enter them? How do you achieve this not once, as a special demonstration of skill, but thousands of times, across the millions of blocks that make up the pyramid structure? The answers require not just skill but methodology, not just talented craftsmen but systematic quality control, not just knowledge of how to work stone, but knowledge of how to verify that the work meets the required standard. The numbers are striking. Consider the logistics alone. The Great Pyramid was built over a period estimated at between 15 and 20 years, based on the length of Khufu's reign. It contains approximately 2.3 million blocks. If we assume a 20-year construction period, that works out to roughly 115,000 blocks per year, or about 315 blocks per day, assuming a work year of 365 days. Other estimates, accounting for seasonal variations in labor availability and the likelihood that work slowed or stopped during the Nile flood, suggest that the daily rate may have been considerably higher during the active construction season. Mark Lehner, one of the foremost living authorities on the Giza pyramids, has estimated that the actual placement rate during peak periods may have exceeded 1 block every 2 to 3 minutes during working hours. This rate of construction implies an extraordinarily well-organized operation. Each block had to be quarried, shaped, transported to the construction site, lifted into position, and fitted into place, all within a system that moved continuously and maintained quality throughout. The quarrying, transport, and placement operations had to be coordinated with military precision. Delays in any part of the process would create bottlenecks that would ripple through the entire operation. The management challenge alone, coordinating thousands of workers across multiple work sites with different tasks and timelines, is formidable by any standard. And this brings us to the first category of lost knowledge that the Great Pyramid represents. Not the knowledge of how to cut stone, though that knowledge is itself remarkable, but the knowledge of how to manage a project of this scale. The organizational knowledge, the logistical knowledge, the ability to plan, coordinate, execute, and maintain quality across a construction project involving millions of individual components, thousands of workers, multiple supply chains, and a timeline measured in decades. This kind of knowledge does not leave physical traces. It lives in the minds of the managers, the planners, the coordinators. It is transmitted through training, through practice, through institutional memory, and it is lost when the institutions that carry it cease to exist. The evolution of pyramid design, from the Step Pyramid of Djoser to the Great Pyramid of Khufu, spans roughly a century, and it tells a story of rapid technological development that is itself a kind of knowledge. The Step Pyramid, built around 2630 before the Common Era, was the first large-scale stone structure in history. It began as a conventional flat-topped mastaba tomb and was enlarged through a series of expansions into a six-stepped structure approximately 62 meters high. The stone blocks used in its construction were relatively small, the size of large mud bricks, reflecting the builder's inexperience with stone as a monumental building material. The architect Imhotep, who is credited with the design, was literally inventing monumental stone architecture as he built. Within a generation, the technology had advanced dramatically. The pharaoh Sneferu, Khufu's father, built at least 3 pyramids during his reign, and the progression from the first to the last shows a rapid learning curve. The Maiden Pyramid, originally built as a step pyramid and later converted into a true pyramid by filling in the steps with a smooth outer layer, partially collapsed at some point, possibly during construction, exposing the stepped core that is visible today. The Bent Pyramid at Dashur, so named because the angle of its sides changes abruptly partway up, reducing from approximately 54 degrees to approximately 43 degrees, is widely interpreted as evidence that the builders recognized a structural problem during construction and reduced the angle to prevent collapse. The Red Pyramid, also at Dashur, was built at the shallower angle of approximately 43 degrees and was completed successfully. It is the first true smooth-sided pyramid and the immediate predecessor of the Great Pyramid. This sequence of structures, spanning perhaps 3 decades, represents one of the most compressed periods of technological learning in human history. In the space of a single generation, the Egyptians went from building a structure that partially collapsed to building one that has stood for more than 4,500 years. They learned from their failures. They adjusted their designs, they refined their techniques, and they accumulated knowledge at a rate that is truly extraordinary. The knowledge accumulated during Sneferu's building program was the foundation on which Khufu's architects built. They inherited not just techniques, but a systematic understanding of what worked and what did not. They knew the angle at which a pyramid becomes unstable. They knew the properties of different types of stone. They knew how to manage the logistics of large-scale construction. They knew how to organize a workforce and maintain quality standards. All of this knowledge, accumulated over decades of intensive building activity, was available to the team that designed and built the Great Pyramid, and this is crucial for understanding the nature of the lost knowledge. The Great Pyramid was not a sudden, inexplicable leap. It was the culmination of a rapid but systematic process of development. Each pyramid built before it contributed knowledge that was incorporated into the next design. The failures were as important as the successes, perhaps more so, because they revealed the limits of existing techniques and motivated the development of new ones. The knowledge that built the Great Pyramid was not the knowledge of a single genius or a single project. It was the accumulated knowledge of an entire building tradition, refined across multiple projects over several decades. This is why the loss of the knowledge is so profound. It was not the loss of a single technique or a single insight. It was the loss of an entire body of accumulated experience, a body of knowledge that had been built up project by project, problem by problem, solution by solution. Recovering such knowledge from the physical evidence alone is like trying to reconstruct a conversation from a photograph of the people who were talking. The photograph preserves the fact that the conversation happened. It preserves the identities of the participants. It even preserves their facial expressions. But it does not preserve the words. And it is the words that mattered. The Wadi al-Jarf papyri, discovered in 2013 by Pierre Tally of the Sorbonne, provide our only direct window into the logistical management of the Great Pyramid project. These papyri, the oldest known in Egypt, were found at a harbour facility on the Red Sea coast and date to the reign of Khufu himself. They include a logbook kept by an inspector named Mera, who was responsible for a team of approximately 200 workers tasked with transporting limestone blocks from the Tura quarries to the Giza construction site. The logbook records daily activities in extraordinary detail. It describes the routes used for transport, the types of boats employed, the quantities of stone moved, and the provisions consumed by the work crew. It mentions a harbour facility near the pyramids, which Talit has identified as a canal basin connected to the Nile, where construction materials were received and staged for movement to the building site. The Wadi al-Jarf papyri confirm what the pyramid itself suggests, that the construction of the Great Pyramid was a logistical operation of enormous scale and sophistication, managed through a bureaucratic system that tracked materials, labour, and supplies with a level of detail that would be recognisable to any modern project manager. But the papyri also reveal how much we do not know. They describe one small part of the operation, the transport of limestone from one quarry. They say nothing about the granite work, the surveying, the placement of blocks at the upper levels, the quality control processes, or the hundreds of other specialised tasks that the construction required. They are a single page from a book that we cannot read, and they are the only page we have. The core problem of the Great Pyramid is not that we lack theories about how it was built. We have dozens of theories. The problem is that none of them fully accounts for the evidence. Each theory explains some aspects of the construction while leaving others unexplained, and the aspects that remain unexplained are precisely the ones that point to the most sophisticated knowledge. Let us begin with the most basic question. How were the blocks lifted into place? The Great Pyramid rises to a height of approximately 138.8 meters in its current state, having lost about 8 meters from its original height due to the removal of the capstone and the uppermost courses. The blocks at the base are the largest, with some weighing more than 6 metric tons. The blocks at the upper levels are smaller, but still substantial, and they had to be raised to heights that would challenge modern crane operators. The granite beams that roof the king's chamber, located roughly 43 meters above ground level, weigh between 25 and 80 metric tons each. Moving these beams from ground level to their final position is one of the most formidable challenges of the entire construction. The most widely accepted theory involves some form of ramp. The simplest version, a straight ramp running from ground level to the top of the pyramid, is mathematically problematic. A ramp with a slope gentle enough to be practical, typically estimated at about 8 to 10 degrees, would need to be more than 1.5 kilometers long to reach the top of the pyramid. The volume of material required to construct such a ramp would be comparable to the volume of the pyramid itself. This does not necessarily rule out the theory, but it does make it difficult to accept as the complete explanation. Jean-Pierre Houdet, a French architect who spent years developing a computer model of the Great Pyramid's construction, proposed in 2007 an alternative theory involving an internal ramp. Houdin suggested that the lower third of the pyramid was built using a conventional external ramp, and that the upper 2/3 were built using a spiral ramp running inside the pyramid structure. He pointed to anomalies detected by microgravity surveys of the pyramid, conducted by a French team in 1986, as evidence for the existence of an internal passage that could represent the remains of such a ramp. Houdin's theory is ingenious and has been well received by many engineers, but it remains unproven. The internal ramp, if it exists, has not been directly observed. But here is the problem. The ramp question, however fascinating, is only about logistics. It is about how millions of blocks were moved. It does not address the far more troubling question of precision, because you can move a block to the right location and still not achieve the tolerances that the Great Pyramid demonstrates. Moving blocks is a problem of force and friction. Fitting blocks is a problem of measurement and craftsmanship, and the craftsmanship displayed in the Great Pyramid is where the truly lost knowledge resides. Consider the King's Chamber. This room, located deep within the pyramid's superstructure, measures approximately 10.47 meters east to west by 5.23 meters north to south by 5.82 meters in height. It is constructed entirely of red granite from Aswan, a stone so hard that it ranks 6 to 7 on the Mohs hardness scale, compared to copper's 3 to 3.5. The walls consist of large granite slabs, carefully dressed and fitted. The ceiling is composed of 9 granite beams, the smallest of which weighs approximately 25 metric tons, and the largest approximately 80 metric tons. These beams span the full width of the chamber without intermediate support. Above them, 5 additional sets of granite beams form a series of stress-relieving chambers designed to distribute the weight of the masonry above and prevent the ceiling from collapsing under the load. The engineering of the stress-relieving chambers is remarkable in itself. The 5 chambers above the King's Chamber were not discovered until 1837, when Colonel Richard William Howard Vyse and the engineer John Shea Perring forced their way into them by blasting through the granite with gunpowder. The uppermost chamber has a gabled roof formed by massive limestone blocks placed at an angle, creating an inverted V that diverts the weight of the overlying masonry to the sides rather than directly onto the flat granite beams below. This is a sophisticated structural solution that demonstrates a clear understanding of load distribution and stress management. The builders knew that the flat ceiling beams could not support the full weight of the pyramid above them. They knew that the load had to be redistributed, and they designed a system to accomplish this that has functioned successfully for more than 4.5 millennia. But the precision of the granite work inside the King's Chamber goes beyond structural engineering. Petrie's measurements revealed that the granite surfaces in the chamber were finished to tolerances of approximately 1/50th of an inch, roughly 0.5 millimeter, over distances of several meters. The surfaces are flat, not roughly flat, not flat enough, flat to a degree that implies the use of some kind of reference surface, a true plane against which the work could be checked. In modern stone masonry, such accuracy is achieved using surface plates, precision ground metal or granite slabs that provide a known flat reference. The ancient Egyptians had no metal that could be precision ground to serve as a surface plate. How then did they verify the flatness of their surfaces? And it gets worse. The sarcophagus in the King's Chamber is a single block of Aswan granite that has been hollowed out to form a rectangular trough. The exterior dimensions are approximately 2.28 meters long, 0.98 meters wide, and 1.05 meters high. The interior was cut to a uniform depth, with walls that are approximately 15 centimeters thick. The surfaces, both interior and exterior, are finished to a high degree of flatness and smoothness, but the truly extraordinary feature is the evidence of the cutting process itself. In the 19th century, Petrie examined the sarcophagus closely and found evidence of saw marks on its exterior surfaces. These marks indicated that the granite had been cut with a large saw, which Petrie estimated at approximately 2.5 meters in length. The saw marks showed consistent pattern that Petrie interpreted as evidence of a fixed-point cutting tool, a blade embedded with cutting material harder than granite, drawn back and forth across the surface. Petrie also examined drill cores recovered from the Giza area, cylindrical pieces of granite that had been removed by tubular drills. These cores bore spiral grooves that Petrie measured carefully. The grooves advanced at a rate that astonished him. In his published analysis, he noted that the feed rate, the rate at which the drill advanced into the granite per revolution, was far greater than what he would have expected from any manual drilling process using known ancient materials. This observation has been a source of controversy for more than a century. The conventional explanation is that the Egyptians used copper tube drills with a loose abrasive, probably quartz sand or emery, fed into the cut as the drill rotated. Experimental replication of this technique has shown that it can cut granite, but the cutting rate achieved in experiments is significantly lower than what Petri's measurements of the ancient drill cores suggest. Christopher Dunn, an engineer and manufacturing specialist, has argued that the ancient drill cores show evidence of cutting rates and pressures that cannot be achieved with hand-powered copper drills and loose abrasive. Dunn's analysis, published in his book The Giza Power Plant and Subsequent Works, suggests that the ancient Egyptians possessed a technology for cutting hard stone that was fundamentally different from, and superior to, anything we have been able to replicate using the tools and methods they are conventionally believed to have used. Dunn's conclusions are controversial. Many Egyptologists reject them, arguing that Petri's original measurements may have been misinterpreted and that experimental replication has distorted the feasibility of copper and abrasive techniques, even if at lower cutting rates. Denai Stocks, a British researcher who has devoted decades to experimental replication of ancient Egyptian stone cutting methods, has demonstrated that copper tools with sand abrasive can cut granite and that the resulting marks are consistent with those found on ancient artifacts. Stocks argues that the key factor is time, that the ancient Egyptians were willing to invest far more time in individual operations than modern experimenters typically devote to their replications. The debate remains unresolved. The evidence from the drill cores and the saw marks is real. The precision of the finished surfaces is real. The question is whether the known ancient toolkit, copper, stone, sand, water, time, and extraordinary patience, is sufficient to explain the evidence, or whether some additional technology, some lost tool or technique, is required. This is not a fringe question. It is a serious technical inquiry that has engaged professional engineers, material scientists, and archaeologists for generations. And the honest answer, the answer that responsible researchers on all sides of the debate will give if pressed, is that we do not know for certain. We have hypotheses, we have experimental results, but we do not have certainty. The question of how the builders maintained the pyramid's geometric accuracy as it rose is among the most challenging to answer. At ground level, the base could be surveyed and checked against reference points on the surrounding terrain. But as the structure grew taller, the working surface moved away from the reference points. Each new course of blocks was laid on top of the previous one, and any error in the placement of one course would be inherited by every course above it. Errors compound. A block that is a fraction of a degree off angle at the base becomes a significant deviation at the top. The fact that the Great Pyramid's overall geometry is so precise implies that the builders had a method for controlling the geometry at every level of the structure, not just at the base. One possibility is that the builders maintained a system of reference marks or benchmarks at the corners and edges of each course, checking the alignment and angle at every stage and correcting any deviation before it could compound. This method, which is standard practice in modern construction, requires precise measuring instruments, a systematic checking procedure, and the organizational discipline to halt construction whenever a deviation is detected and to correct it before proceeding. The fact that the finished pyramid meets such tight tolerances suggests that such a system was in place and was followed rigorously throughout the construction. Another possibility is that the builders used an external reference, such as a plumb line dropped from a fixed point high above the construction site to maintain vertical alignment. Some researchers have proposed that wooden scaffolding or permanent stone structures at the pyramid's corners served as reference frames against which the rising masonry could be checked. No direct evidence of such structures has been found, but the absence of evidence is not evidence of absence. Temporary structures would have been removed after construction was complete, leaving no trace. Whatever method was used, it had to be reliable, consistent, and usable under the conditions of an active construction site. The building surface at the upper levels of the pyramid was a hostile working environment, exposed to wind, sun, and the physical hazards of working at height on a steep, irregular surface. The measuring instruments had to be portable, durable, and accurate under these conditions. The workers who used them had to be skilled, attentive, and meticulous. The supervisors who oversaw the process had to be experienced enough to recognize deviations and authoritative enough to halt work when corrections were needed. The entire quality control system was a form of knowledge that was as important as the construction techniques themselves. And like those techniques, it has been lost. The question of ancient Egyptian astronomy and its relationship to the pyramid's design opens another avenue of inquiry into lost knowledge. The Egyptians were careful observers of the night sky. Their calendar was based on the heliacal rising of the star Sirius, the brightest star in the sky, whose appearance just before dawn coincided approximately with the beginning of the Nile flood. They identified and named constellations, mapped the movements of the planets, and divided the night sky into 36 decans, 10-degree segments that were used for timekeeping. This astronomical knowledge was intimately connected to their religious beliefs. The pharaoh's afterlife journey was mapped onto the sky. The constellation we call Orion was associated with the god Osiris. The circumpolar stars, which never set below the horizon, were called the imperishable ones and were associated with eternity. The so-called star shafts of the Great Pyramid, narrow channels that extend from the king's chamber and the queen's chamber to the exterior of the pyramid at specific angles, have been interpreted by some researchers as having astronomical significance. The south shaft of the king's chamber points approximately toward the position of the star Alnitak in Orion's belt as it crossed the meridian in the pyramid's era. The north shaft of the king's chamber points approximately toward the pole star of the era, the star Thuban in Draco. These alignments, first identified by the astronomers Virginia Trimble and Alexander Badovy in 1964, suggest that the shafts may have been designed to connect the pharaoh's burial chamber symbolically with specific stars associated with the afterlife. Whether these alignments are intentional or coincidental remains debated. The angles of the shafts are not perfectly precise for any specific star, and the difficulty of sighting a star through a long, narrow, angled tube has led some researchers to question whether the shafts could have served as practical astronomical instruments. But even the approximate alignment suggests that the builders possessed the astronomical knowledge necessary to calculate the angles at which specific stars would be visible from the pyramid's latitude at specific times of day. This knowledge, the ability to translate celestial observations into construction parameters, is another dimension of the capability that has been lost. The relationship between the Great Pyramid and the broader field of ancient Egyptian scientific knowledge is complex and still being explored. The Rhind mathematical papyrus, written around 1650 before the Common Era, but believed to be a copy of an older Middle Kingdom text, contains mathematical problems that include calculations of pyramid volumes and slope angles. Problem number 56 in the papyrus specifically deals with the calculation of the sect, the Egyptian measure of slope, for a pyramid of given height and base width. The seat was expressed as the horizontal displacement per cubit of vertical rise, a measure that is directly analogous to the modern concept of slope or gradient. The fact that the Rhind papyrus includes problems related to pyramid geometry suggests that such calculations were a standard part of the mathematical curriculum, at least during the Middle Kingdom. Whether similar texts existed during the Old Kingdom when the Great Pyramid was built is unknown, because no mathematical papyri from that period have survived. The stonework at Giza extends far beyond the king's chamber. The casing stones that originally covered the exterior of the Great Pyramid were made of fine white Tura limestone, quarried from the eastern bank of the Nile and transported across the river by barge. These stones were cut to precise angles to form the smooth, sloping outer surface of the pyramid. The angle of the pyramid's faces, approximately 51 degrees and 52 minutes, is consistent across all four sides. This consistency required that each casing stone be cut to the same angle, a process that demands either extraordinary individual skill or a standardized system of measurement and verification. Petrie found that the surviving casing stones at the base of the pyramid were fitted with joints averaging approximately 1/50th of an inch, about 0.5 millimeter, across surfaces that extended for more than a meter. The surfaces were not merely close, they were optically flat, meaning that if a straight edge were placed on them, no gap would be visible to the naked eye. This degree of flatness, achieved on limestone blocks weighing several tons, is extraordinary by any standard. It implies not just skilled labor, but quality verification. Some method of checking the flatness and fit of each block before it was set in place. The mortar used in these joints has been analyzed chemically and found to be a gypsum-based material that is harder than the limestone blocks themselves. The mortar was not used to fill gaps. It was used, as Petri noted, as a lubricant to facilitate the precise placement of the blocks. This is a critical insight. The builders were not using mortar to compensate for imprecision. They were using it to enable precision. The mortar allowed the blocks to be slid into position against each other without friction damage to the contact surfaces. This implies a placement process that was designed for precision from the outset, not one that achieved precision as an incidental byproduct of general construction. There is an additional dimension to the granite work that raises questions about the builder's knowledge of materials science. Granite is an igneous rock composed primarily of quartz, feldspar, and mica. Quartz, the hardest of these minerals, ranks 7 on the Mohs hardness scale. Copper ranks 3 to 3.5. Theoretically, copper cannot cut quartz. In practice, the addition of an abrasive medium, typically quartz sand, transforms the copper tool from a cutting instrument into a holding device for the abrasive particles, which do the actual cutting. The copper tube holds the abrasive against the stone, and the rotational motion grinds away the material. This process works. Experimental replication has confirmed that it works, but it works slowly. The question of how slowly raises one of the persistent puzzles of pyramid construction. If the known method of cutting granite with copper and sand is the method that was used, then the time required to produce the granite elements of the Great Pyramid, the king's chamber walls, the ceiling beams, the sarcophagus, the plugging blocks, and the stress-relieving chambers must have been enormous. Each surface had to be ground flat. Each block had to be shaped to precise dimensions. Each beam had to be finished to a standard that modern measurements confirm was extraordinary. The cumulative labor of grinding, one abrasive particle at a time, across thousands of square meters of granite surface is staggering, and the precision of the finished product compounds the puzzle. Grinding with loose abrasive is an inherently imprecise process. The abrasive particles are randomly sized and randomly distributed. They cut unevenly, leaving a surface that is rough and irregular at the microscopic level. Achieving a flat surface by this method requires repeated cycles of grinding, checking, and correcting, each cycle removing less material and producing a finer surface. The final stages of this process are extremely slow because the amount of material being removed is tiny and the checking process is laborious. To achieve the tolerances that Petri documented, tolerances of 1/50th of an inch or better, across surfaces of several square meters, would require hundreds or thousands of checking and correction cycles. Each cycle would need to identify the high spots on the surface, mark them, grind them down, and recheck. The time investment is enormous, the skill required is extraordinary, and the checking process itself requires a reference surface of known flatness, which raises the question of how such a reference was created. In modern precision manufacturing, flat reference surfaces are created through a process called three-plate lapping, in which 3 surfaces are ground against each other in alternating pairs. The mutual grinding process eliminates curvature, because any deviation from flatness on one surface is reflected as an irregularity on the others, and the alternating pairing ensures that all 3 converge toward a true plane. This process requires no external reference. It is self-correcting. Whether the ancient Egyptians knew of this technique or something analogous to it is unknown, but the precision of their finished surfaces implies that they had some method of achieving and verifying flatness to a high standard. That method is lost. The construction of the descending passage presents another puzzle. This passage was cut through the bedrock of the Giza Plateau for approximately 29 meters, then continued through built masonry for approximately 77 meters, maintaining its angle of 26 degrees and 31 minutes throughout. The bedrock portion was cut from above before the pyramid was built over it. The masonry portion was built around the passage as the pyramid rose. The two portions had to align perfectly, which meant that the angle and direction of the bedrock cutting had to match precisely the planned angle and direction of the masonry construction above. Any error in the bedrock cutting would have propagated upward through the entire pyramid. The level of planning required for this kind of integrated construction is exceptional. The builders had to conceive of the entire internal structure of the pyramid before they began building. They had to locate every passage, every chamber, every void in three-dimensional space and translate those locations into a construction sequence that built the structure from the bottom up while maintaining precise alignment at every stage. This is not simple planning. This is what modern engineers call systems engineering, the discipline of managing complex projects in which multiple subsystems must be designed, built, and integrated into a functioning whole. The ancient Egyptians practiced systems engineering on a scale that would not be matched for millennia. But here is what makes this truly terrifying. The Great Pyramid is not the only pyramid at Giza. It is one of three major pyramids, along with smaller Queen's pyramids, mastaba tombs, and an extensive complex of causeways and temples. The second pyramid, attributed to Khafre, and the third, attributed to Menkaure, also display high levels of precision, though not quite at the level of the Great Pyramid. And beyond Giza, more than 100 pyramid sites have been identified in Egypt, spanning a construction tradition that lasted for more than 1,000 years. The earliest pyramid, the Step Pyramid of Djoser at Saqqara, was built approximately a century before the Great Pyramid. The last major pyramids were built during the Middle Kingdom, more than 500 years after the Great Pyramid. This timeline reveals something crucial about the lost knowledge. The Great Pyramid represents the peak of the tradition. The pyramids built before it, including the Bent Pyramid and the Red Pyramid at Dashur, show a rapid progression in skill and ambition. The pyramids built after it show a gradual decline. The 5th Dynasty pyramids at Abusir are smaller, less precisely built, and constructed with inferior materials. The Middle Kingdom pyramids are smaller still, many built with mud brick cores rather than stone. The knowledge that peaked with the Great Pyramid was already being lost within a few generations of its construction. By the New Kingdom, more than 1,000 years later, the Egyptians had stopped building pyramids altogether. The trajectory is unmistakable: a rapid development of skill, a peak of achievement, a gradual decline, and then cessation. The knowledge was not maintained. It was not passed down intact from generation to generation. It eroded. Each generation of pyramid builders was slightly less capable, slightly less ambitious, slightly less precise than the one before. The institutional knowledge that had made the Great Pyramid possible was depleted over time, not replenished. And eventually, it was gone. The quest to understand how the Great Pyramid was built has attracted some of the most brilliant and most eccentric minds in history. From the Greek historian Herodotus, who visited Egypt in the 5th century before the Common Era and recorded the first known account of the pyramid's construction, to the modern engineers and physicists who study it with lasers and ground-penetrating radar, the Great Pyramid has been a canvas onto which each generation projects its own assumptions and anxieties about what is possible. Herodotus, writing more than 2,000 years after the pyramid was built, described a construction method involving machines made of short pieces of wood that were used to lift the blocks from one level to the next. His account, which was based on conversations with Egyptian priests who were themselves separated from the pyramid builders by 2 millennia, is vague enough to support multiple interpretations. Some have read his description as referring to lever-like devices. Others have interpreted it as referring to some form of crane or hoist. The truth is that Herodotus was reporting hearsay from a source that was itself relying on oral tradition rather than technical documentation. His account is valuable as evidence that the construction method was already unknown in his time, but it cannot be relied upon for technical accuracy. The problem of the ramp has generated more theories than perhaps any other single question in archaeology. We have already discussed the straight ramp and Jean-Pierre Houdin's internal ramp, But there are many other proposals. The spiral ramp theory, in which a ramp winds around the outside of the pyramid as it rises, is one of the oldest and most intuitive solutions. It accounts for the decreasing area at each level and allows construction to proceed at all levels simultaneously. But it has problems. A spiral ramp would obscure the corners of the pyramid during construction, making it impossible to check the alignment and geometry of the structure as it rose. For a building whose defining feature is its geometric precision, the inability to verify that geometry during construction would be a serious drawback. Dieter Arnold, a German Egyptologist who spent decades studying Egyptian construction methods, proposed a model involving multiple small ramps positioned at various points around the pyramid, each serving a specific section of the structure. Arnold's approach, detailed in his comprehensive study Building in Egypt, published in 1991, draws on extensive archaeological evidence from multiple pyramid sites and represents one of the most careful and evidence-based analyses of the construction problem. He emphasized that no single method was likely used for the entire pyramid. Different stages of construction and different components of the structure probably require different techniques. The base courses, where the blocks are largest and heaviest, would have required different handling than the upper courses, where the blocks are smaller but the vertical distance is greater. Arnold's principle that the construction involved multiple methods adapted to specific challenges is almost certainly correct, but it also highlights the depth of the knowledge required. The builders had to know not just one method of moving and placing stone, but many. They had to know when to apply each method. They had to know the limitations of each approach and how to adapt when conditions changed. This is not the knowledge of a simple construction technique. It is the knowledge of a comprehensive engineering methodology, a flexible, adaptive system of practices that could be applied to a wide range of problems. The water hypothesis represents another important line of inquiry. Several researchers, most notably the French materials scientist Joseph de Davids and the more recent work of the physicist Daniel Bonn at the University of Amsterdam, have proposed that water played a crucial role in moving the pyramid blocks. Bonn's research, published in 2014 in the journal Physical Review Letters, demonstrated through laboratory experiments that wetting the sand in front of a sledge reduces the friction coefficient by approximately 50%, cutting the force needed to pull the sledge in half. Bonn noted that an ancient Egyptian tomb painting from the tomb of Jehuti-Hotep, dated to approximately 1880 before the Common Era, shows a worker pouring water in front of a sledge, carrying a large statue. This image, Bonn argued, was not merely ceremonial, but depicted an actual construction technique. The water-on-sand hypothesis is elegant and experimentally supported, but it addresses only the horizontal transport of blocks. It does not explain how blocks were raised vertically, and it does not explain the precision aspects of the construction. Sliding a block on wet sand is a method for moving large masses, not for placing them with millimeter accuracy. The transport problem and the precision problem are related but distinct, and solutions to one do not necessarily address the other. Davidovits went even further. Beginning in the 1970s, he proposed that many of the pyramid blocks were not cut from natural stone at all, but were cast in place from a limestone concrete, a mixture of crusite limestone, water, natron, and other materials that could be poured into molds and allowed to harden. Davidovits, who is a pioneer in the development of geopolymer materials, argued that casting would explain the remarkable fit between blocks, since the wet concrete would conform to the surface of adjacent blocks as it hardened. He also pointed to chemical and microstructural analyses of pyramid blocks that he claimed showed evidence of synthetic composition, including the presence of minerals and air bubbles that would not be found in naturally quarried limestone. The geopolymer theory has been fiercely debated. Dipayan Jana, a petrographer who analyzed pyramid limestone samples in 2007, concluded that the blocks showed clear evidence of natural geological origin, including fossils, sedimentary layering, and mineral composition consistent with the Giza Plateau's geological formation. Janna's analysis, published in a detailed technical report, found no evidence of synthetic or reconstituted stone. Other researchers have reached similar conclusions. The majority view in the geological and archaeological communities is that the pyramid blocks are natural stone, not cast concrete. But Davidovitz's theory, even if incorrect in its specific claims, raised an important methodological point: the assumption that we fully understand the materials and techniques used in pyramid construction is just that, an assumption. And assumptions, when applied to a structure that consistently exceeds our expectations, deserve scrutiny. The math is striking. Consider the internal geometry of the pyramid. The passages and chambers within the Great Pyramid are aligned with extraordinary precision. The descending passage, which enters the pyramid from the north face and runs downward at an angle of approximately 26 degrees and 31 minutes, maintains this angle with minimal deviation over a length of more than 100 meters, including sections cut through bedrock and sections built within the masonry. Maintaining a consistent angle over that distance, in a passage only about 1 meter wide and 1.2 meters high, requires continuous measurement and correction during construction. The builders had to check the angle at every stage and correct any deviation before it compounded. The Grand Gallery, one of the most impressive interior spaces in the Great Pyramid, rises at the same angle as the ascending passage, approximately 26 degrees and 31 minutes, and extends for approximately 46.7 meters. Its walls are cobelled, meaning that each successive course of stone projects slightly inward from the one below, creating a narrowing passage that is approximately 8.7 meters high at its maximum. The corbelling is uniform and symmetrical, with each course projecting approximately 7.6 centimeters beyond the one below. This level of regularity, maintained across more than 46 meters of sloping construction, requires extraordinary control of the building process. The angle of the passages, approximately 26 degrees 31 minutes, is worth noting because it is close to the angle that would allow a viewer standing at the entrance to the descending passage to see the North Celestial Pole. This has led to speculation that the passage was designed as an astronomical observation tube, aimed at the pole star of the era, possibly the star Thuban in the constellation Draco. Whether this alignment was intentional or coincidental is debated, but the precision of the angle is itself significant. It demonstrates that the builders could maintain a specific angle over a long distance with a high degree of accuracy. Let us consider the knowledge of mathematics embedded in the pyramid. The ratio of the pyramid's perimeter to its height is approximately 6.283, a value remarkably close to 2 times pi, the mathematical constant that relates the circumference of a circle to its diameter. Whether the builders intentionally encoded this relationship in the pyramid's proportions, or whether it emerged incidentally from the use of a specific slope angle, has been debated for more than a century. The mathematician John Taylor first proposed the pi theory in 1859, and it was subsequently championed by the astronomer Charles Piazzi Smith. The relationship holds to within 0.1%. Many scholars dismiss it as coincidental, arguing that the builders were working with slope ratios, not abstract mathematical constants. Others note that the Egyptians were certainly capable of measuring circles and calculating their properties, as evidenced by the mathematical knowledge documented in the Rhind mathematical papyrus, dated to approximately 1650 before the Common Era, which includes a method for calculating the area of a circle that implies an effective approximation of pi at 3.16, accurate to within 1%. The debate over the mathematical knowledge embedded in the pyramid illustrates a broader problem with interpreting ancient achievements. When we find a precise relationship in an ancient structure, we face a choice. Either the builders intended the relationship, which implies they possessed the mathematical knowledge to create it, or the relationship is a coincidence, which implies that we are reading meaning into random data. In the case of the Great Pyramid, the precision of the measurement makes coincidence less likely, but not impossible, and the absence of textual evidence that the builders understood pi as an abstract concept makes intentionality difficult to prove. What we can say with confidence is this: The builders of the Great Pyramid possessed practical mathematical knowledge of a very high order. They could calculate slopes, angles, and volumes. They could lay out large-scale geometric forms with extraordinary accuracy. They could maintain consistent proportions across a structure containing millions of individual components. Whether they understood the abstract mathematical principles underlying their practical techniques is a separate question, and one that the physical evidence alone cannot answer. The experimental archaeology program at the Nova Lerna project attempted to address some of these questions by building a small pyramid using techniques consistent with what is known about ancient Egyptian methods. In 1997, Mark Lehner organized a team of workers to construct a miniature pyramid approximately 6 meters high using limestone blocks, copper tools, and simple mechanical devices. The project demonstrated that the basic operations of quarrying, transporting, and placing limestone blocks were feasible with ancient technology. But the mini-pyramid was a tiny fraction of the size of the Great Pyramid, and the team did not attempt to achieve the precision that characterizes the original. The experiment confirmed that pyramid construction was possible with ancient tools, but did not address the question of precision that lies at the heart of the mystery. The thermal behavior of the Great Pyramid has been studied using modern imaging technology and has yielded puzzling results. In 2015, the Scan Pyramids project, an international collaboration involving researchers from Egypt, France, Japan, and Canada, conducted a thermal imaging survey of the pyramid's exterior. The survey, which measured the temperature of the pyramid's surface at different times of day, revealed a thermal anomaly on the eastern face of the pyramid at ground level. 3 adjacent blocks showed a significantly higher temperature than their neighbors, suggesting that the area behind them was structurally different from the surrounding masonry, perhaps containing a void or a passage. The anomaly has not been explained, and no excavation has been conducted to investigate it. The thermal survey is one of several non-invasive investigations that have been conducted on the Great Pyramid in recent years. In addition to the muon tomography that detected the large void above the Grand Gallery, researchers have used ground-penetrating radar, microgravity measurements, and infrared thermography to image the pyramid's interior. These studies have revealed that the pyramid's internal structure is more complex than previously thought. There may be voids, passages, and chambers that remain undiscovered. There may be structural features that shed light on the construction methods used. The difficulty is that investigating these features without damaging the pyramid is extremely challenging, and the Egyptian authorities are understandably cautious about authorizing invasive investigations. The question of what lies hidden inside the Great Pyramid is closely connected to the question of lost knowledge. If there are undiscovered chambers or passages, they may contain artifacts or inscriptions that could illuminate the construction process. The relieving chambers above the King's Chamber, when they were opened by Vyse in 1837, revealed quarry marks and gang names painted on the granite blocks, providing some of the only direct evidence linking the pyramid to Khufu's reign. If similar markings exist in other undiscovered spaces, they could provide invaluable information about the construction timeline, the organization of the workforce, and the techniques used at different stages of the building process. Let us now turn to a fascinating but often overlooked aspect of pyramid construction: the optical properties of the original exterior. The casing stones that covered the Great Pyramid's exterior were made of fine white Tura limestone, a high-quality stone with a smooth, dense surface that could be polished to a near-mirror finish. When the pyramid was new, its surfaces would have reflected sunlight with dazzling intensity, visible for dozens of kilometers across the desert. Some ancient accounts describe the pyramid as appearing to glow or shine, an effect entirely consistent with polished white limestone in the intense Egyptian sun. The production of these casing stones required a level of stoneworking skill that is distinct from the skill needed for the core blocks. The casing stones had to be cut to precise angles to form the pyramid's sloping surfaces. They had to be finished to optical flatness on their outer faces, and they had to be fitted to each other with the extraordinarily tight joints that Petri documented. Each casing stone was, in effect, a precision-machined component that had to meet three different quality standards simultaneously: the angle, the surface finish, and the fit. The production of tens of thousands of such components to a consistent standard represents a manufacturing achievement of the first order. The casing stones are now almost entirely gone. They were stripped from the pyramid primarily during the medieval period and used in the construction of mosques and other buildings in Cairo. The few remaining casing stones at the base of the pyramid's north face provide the only surviving evidence of the original exterior finish. These survivors confirm Petri's measurements and demonstrate that the original surface was indeed finished to a degree of precision that is extraordinary for hand-worked stone. The loss of the casing stones is itself a metaphor for the loss of knowledge. The most visible, most impressive, most immediately recognizable feature of the Great Pyramid has been removed. What remains is the rough core masonry, which, while still monumental, gives only a partial impression of what the original structure looked like. Visitors to Giza today see a pyramid that has been stripped of its outer skin, reduced to its structural skeleton. They see the bones, not the body, and in the same way, the knowledge that survives about the pyramid's construction is the skeletal outline of a much richer and more detailed body of understanding that has been lost. One more theory deserves consideration, not because it provides the final answer, but because it illustrates the difficulty of the problem. The French architect Gilles Dormion has conducted extensive studies of the internal structure of the Great Pyramid using non-invasive techniques, and has proposed that the internal layout is far more complex than the known passages and chambers suggest. Dormion believes that the king's chamber, despite its name, was not the primary burial chamber, and that the pharaoh's actual burial place remains undiscovered, hidden behind the walls of the known structure. His theory is based on detailed analysis of structural anomalies, including cracks in the granite ceiling beams of the king's chamber that suggest the room was subjected to stresses beyond what would be expected from the overlying masonry alone. Whether Dormion is correct remains to be determined, but his work highlights a fundamental point about the Great Pyramid. After more than 2 centuries of systematic study, using technologies that range from Petri's handmade measuring instruments to cosmic ray detectors and thermal imaging cameras, we are still discovering new features and revising our understanding of the structure's internal layout. The pyramid has not yielded all its secrets, and the knowledge required to build it has not been fully reconstructed. This distinction between what is possible and what was actually achieved is critical. It is possible to build a pyramid with copper tools and simple ramps. What appears not to be possible, at least not with the methods demonstrated in modern experiments, is to build a pyramid with the Great Pyramid's specific level of precision. The gap between the demonstrated capability of replicated ancient methods and the documented accuracy of the actual structure remains unexplained, and in that gap lies the lost knowledge. wcwhomeclaude.gpscrike.md. There is yet another domain of lost knowledge that the Great Pyramid illuminates, one that has received insufficient attention in the popular literature: the knowledge of rock mechanics. The builders of the Great Pyramid did not merely stack blocks. They managed the structural behavior of millions of tons of stone under gravitational load. They understood, at least empirically, how stone behaves when compressed, how cracks propagate through a loaded structure, and how stress can be redistributed through geometric design. The evidence for this understanding is visible in the stress-relieving chambers above the king's chamber. These 5 chambers, stacked vertically above the flat ceiling of the king's chamber, serve no other purpose than to distribute the weight of the overlying masonry so that it does not bear directly on the ceiling beams. The topmost chamber has a gabled roof, a design that converts vertical load into lateral thrust, pushing the weight sideways rather than allowing it to press downward on the flat beams below. This is a sophisticated structural solution that demonstrates a clear understanding of force distribution in a loaded structure. But the stress-relieving chambers also reveal something about the limits of the builder's knowledge. The granite beams that ceiling the king's chamber are cracked. At least 2 of the 9 beams show visible cracks that extend partially through their thickness. These cracks occurred during or shortly after construction, probably when the enormous weight of the masonry above was first applied to the beams. The relieving chambers prevented the cracked beams from collapsing, but the fact that the beams cracked at all suggests that the builders' calculations were imperfect. They had underestimated the load, or overestimated the strength of the beams, or both. The stress-relieving chambers may have been an adaptation, a solution to a problem that was discovered during construction rather than anticipated in the design. This interpretation, if correct, is profoundly illuminating. It suggests that the builders of the Great Pyramid were not working from a complete theoretical understanding of structural mechanics. They were working from empirical knowledge, from rules of thumb developed through experience, and they were capable of making errors. But when errors occurred, they had the knowledge and the organizational flexibility to devise solutions on the fly. They could diagnose a structural problem and implement a fix within the ongoing construction process. This adaptive capability, the ability to respond to unexpected problems with effective solutions, is one of the most valuable forms of engineering knowledge and one of the most difficult to preserve. It depends not on written rules but on experienced judgment. The exterior geometry of the pyramid reveals yet another layer of knowledge. The four faces of the Great Pyramid are not perfectly flat planes. They are very slightly concave, meaning that each face is slightly indented along its center line, creating a subtle effect that is virtually invisible to the naked eye, but detectable through careful measurement and under certain lighting conditions through aerial photography. The degree of concavity is extremely small, amounting to a deviation of less than 1 meter from a flat plane across the full width of the face. This feature was first noted by I.E.S. Edwards, a leading authority on Egyptian pyramids, and has been confirmed by subsequent surveys. The purpose of this concavity, if it is intentional, is unknown. Some researchers have suggested that it was a structural feature designed to increase the stability of the casing stones. Others have proposed that it was an aesthetic choice, creating a subtle play of light and shadow on the pyramid's surface that would have been visible when the casing was intact. Still others believe it may be an artifact of the construction method, a natural consequence of the way the courses were laid and the casing stones were fitted. Whatever its origin, the concavity demonstrates either an extraordinary degree of intentional control over the pyramid's geometry or an extraordinary degree of consistency in the construction process. Either way, it represents knowledge that we cannot fully explain. There is another category of lost knowledge that deserves examination, and it is perhaps the most fundamental of all. It is the knowledge of the workforce itself. The hands-on, practical, bodily knowledge of the masons, the surveyors, the quarrymen, and the foremen who actually did the work. This is knowledge that exists not in texts or drawings, but in muscles, in eyes, in the calibrated judgment of a craftsman, who can tell by touch whether a surface is flat, by sound whether a stone is sound, by feel whether a tool is cutting correctly. This embodied knowledge, this craft knowledge, is the most difficult to transmit and the most impossible to recover once lost. Consider what a master mason working on the Great Pyramid would have known. He would have understood the properties of different types of stone, their grain, their cleavage, planes, their response to different cutting techniques. He would have known how to read the stone, to anticipate where it would crack and where it would hold. He would have known how to maintain and sharpen his tools, how to adjust his technique to compensate for tool wear, how to achieve a consistent quality of finish across surfaces of varying hardness and composition. He would have known the feel of correct work, the sound of a clean cut, the visual cues that indicated whether a surface was true. And he would have learned all of this not from a textbook, but from years of apprenticeship under a more experienced craftsman who had learned it from his predecessor in a chain of transmitted skill that stretched back through generations. When the pyramid building tradition ended, that chain was broken. The master masons who had worked on the last pyramids passed their skills to their apprentices, but those apprentices were set to work on different projects, temples, tombs, smaller monuments, that did not require the same degree of precision. Over time, the most refined skills, the ones that were specific to large-scale precision stonemasonry, atrophied through disuse. The general knowledge of stoneworking persisted. The Egyptians continued to produce magnificent stone architecture for millennia after the Pyramid Age. But the specific, extreme, almost obsessive precision that characterizes the Great Pyramid was not maintained. It could not maintained because the conditions that had produced and sustained it, the constant demand for that level of quality, the institutional support for the training that produced it, no longer existed. This is a pattern that is observed in every craft tradition. Skill that is not practiced decays. Knowledge that is not transmitted disappears. The most refined capabilities of any craft, the ones that require years of dedicated practice to develop and maintain, are the first to be lost when the demand for them declines. The Great Pyramid represents the peak of a craft tradition that required generations to develop and that began to erode almost immediately after it was no longer needed. The knowledge was not taken away. It was not suppressed. It simply evaporated, like water from a pool that is no longer replenished. Let us also consider the broader context of ancient knowledge systems that have been lost and partially recovered, because the Great Pyramid's lost knowledge does not exist in isolation. The Antikythera mechanism, recovered from a shipwreck off the coast of the Greek island of Antikythera in 1901, is a complex bronze device consisting of approximately 30 interlocking gears. Analysis using X-ray computed tomography has revealed that the mechanism was an astronomical calculator capable of predicting eclipses, tracking the positions of the sun and moon, and modeling the irregular motion of the moon using a sophisticated gear train. The device dates to approximately 100 to 150 before the Common Era, and it demonstrates a level of mechanical sophistication that was not seen again in the European tradition until the astronomical clocks of the 14th century of the Common Era. The knowledge required to design and build the Antikythera mechanism, the understanding of gear ratios, the ability to machine bronze to precise tolerances, the astronomical knowledge to model celestial motions, all existed in the ancient world and was lost. The Roman formula for hydraulic concrete, the volcanic ash-based material that allowed the Romans to build structures underwater, and that gives the Pantheon in Rome its remarkable durability, was lost after the fall of the Western Roman Empire and was not rediscovered until the 18th century. The concrete of the Pantheon's dome, poured more than 1900 years ago, remains the largest unreinforced concrete dome in the world. An analysis of its composition has revealed that the Romans used a carefully graded mixture of aggregates, with lighter pumice near the top and heavier basalt near the base, to reduce the weight of the dome while maintaining structural integrity. This was not accidental. It was the product of generations of engineering knowledge. The Damascus steel of the medieval Islamic world, famous for its distinctive watered pattern and its remarkable combination of hardness and flexibility, was produced by a process that was lost by the 18th century and has never been fully replicated. Modern analysis of Damascus steel blades has revealed the presence of carbon nanotubes and cementite nanowires within the steel's microstructure, features that modern materials scientists can create intentionally, but that medieval smiths produced through empirical processes they developed over centuries of practice without any understanding of the underlying science. These examples share a common pattern with the Great Pyramid. In each case, ancient or medieval craftspeople achieved results that modern science can measure and admire, but cannot fully explain or replicate using the tools and methods believed to have been available. In each case, the knowledge was practical, embodied, developed through generations of trial and refinement. In each case, the knowledge was lost when the institutional, economic, or cultural conditions that sustained it changed. And in each case, recovery of the knowledge has been partial at best, because practical knowledge cannot be fully reconstructed from the physical evidence it leaves behind. You can analyze a Damascus steel blade down to the nanometer scale, and you still cannot recreate the process that produced it, because the process was a sequence of actions, temperatures, timings, and judgments that existed in the hands and minds of smiths who died centuries ago. The question of construction management at the Great Pyramid has been illuminated by the discovery of the workers' village at Giza. Excavations by Mark Lehner and Zahi Hawass, conducted over multiple seasons beginning in the late 1980s, revealed an extensive settlement southeast of the Sphinx that housed the permanent workforce responsible for the pyramid's construction. The village included barracks capable of housing up to 2,000 workers, bakeries producing enough bread to feed the entire labor force, breweries producing the beer that was a staple of the Egyptian diet, workshops for tool production and repair, and medical facilities where workers received treatment for injuries and illnesses. The bakeries alone reveal the scale of the support operation. Lehner's team estimated that the bakeries at the workers' village could produce several thousand loaves of bread per day. The bread was made from emmer wheat, ground on stone saddle querns, and baked in bell-shaped clay molds called bedja. The production process, from grain to finished loaf, involved grinding, sieving, mixing, fermentation, and baking, each step requiring specialized knowledge and equipment. The bakeries operated continuously, feeding a workforce that consumed prodigious quantities of food. Analysis of animal bones found at the site revealed that the workers received a diet rich in meat, including beef, the most prestigious food in ancient Egypt. This was not the diet of slaves. It was the diet of a valued workforce being maintained at the state's expense. The medical evidence from the workers' village is equally revealing. Skeletal analysis of worker burials shows that many individuals suffered injuries consistent with heavy manual labor, including compression fractures of the spine, healed bone breaks, and degenerative joint disease. But it also shows evidence of medical treatment. Fractures had been set and splintered. Amputations had been performed and survived. One individual showed evidence of a surgical procedure on the skull, a trepanation which had healed successfully. The workers were not disposable labor. They were invested in, they were cared for. And this investment itself represents a form of knowledge, the knowledge of how to maintain a workforce's health and productivity over the long duration of a massive construction project. The organization of the workforce into named teams, as evidenced by graffiti found on pyramid blocks and in the workers' village, adds another dimension to our understanding of the management system. The teams had names like Friends of Khufu and Drunkards of Menkaure. They were organized into divisions called files, each led by an overseer. The competitive element suggested by the graffiti, with teams recording their achievements, implies a management strategy that used group identity and rivalry to motivate performance. This is organizational psychology applied to construction management more than 4,000 years before the term was coined. The copper tools themselves deserve a final word. More than 1,000 copper artifacts have been recovered from Old Kingdom contexts, including chisels, adzes, saw blades, and drill bits. These tools show evidence of careful manufacture and deliberate design. The chisels were cast in molds and then cold hammered to harden the cutting edge, a process that increases the hardness of copper from approximately 3 on the Mohs scale to approximately 4, still well below the hardness of granite, but adequate for working softer stones like limestone and alabaster. The saw blades were long, flat strips of copper with teeth cut along one edge. Some show evidence of having been used with abrasive, their teeth worn smooth by the sand or emery that did the actual cutting. These tools represent a technology that was optimized for the materials available. Copper is not an ideal tool material. It is soft, it wears quickly, it must be frequently resharpened. But it was the hardest metal available to the Old Kingdom Egyptians, who had not yet developed bronze alloys. Working within this limitation, the Egyptians developed techniques that extracted the maximum performance from a mediocre material. Their copper tools were not primitive. They were the products of a sophisticated understanding of metallurgy and materials behavior, optimized through generations of refinement for the specific tasks of quarrying, cutting, and finishing stone, and the knowledge of how to make and use these tools, of how to select the right tool for the right material, of how to maintain a cutting edge under demanding conditions, was an essential part of the knowledge system that built the Great Pyramid. The Great Pyramid's lost knowledge belongs in this category. It was practical knowledge, It was embodied knowledge. It was refined over generations. And it was lost not because of catastrophe or conquest, but because of the ordinary, relentless, almost invisible process of knowledge decay that afflicts every society whose conditions change. The deeper truth about the lost knowledge of the Great Pyramid is not about ancient Egypt at all. It is about the nature of knowledge itself. And it begins with a distinction that most people have never considered: the distinction between information and capability. Information is what can be written down. It is data, facts, measurements, procedures, descriptions. It can be stored in texts, encoded in symbols, preserved in libraries. It can be transmitted across distances and across generations without degradation, provided the medium of storage is maintained and the language is understood. Information is durable, it is copyable, it is in principle immortal. Capability is something else entirely. Capability is the ability to do something, to cut granite with precision, to lay out a building aligned to true north, to manage a workforce of thousands across a 20-year construction project. Capability is not information. It includes information, but it also includes skill, judgment, experience, institutional knowledge, organizational systems, and the thousand small adjustments that a practitioner makes in the course of doing work that cannot be specified in advance. Capability is fragile. It is not copyable. It exists only in the people and institutions that possess it, and it dies with them if it is not transmitted. The Great Pyramid is proof that the ancient Egyptians possessed extraordinary capability. The physical evidence is irrefutable. The precision of the construction, the scale of the logistics, the sophistication of the engineering, all demonstrate a level of capability that was among the highest ever achieved by any pre-industrial civilization. But capability, unlike information, does not preserve itself. It must be actively maintained through practice and transmission. When the practice stops and the transmission breaks, the capability vanishes, leaving behind only the products it created and the information that can be extracted from them. This is why the Great Pyramid is so much more than a historical curiosity. It is a monument to the fragility of human achievement, a reminder that the most impressive things we can do are also the most ephemeral. The pyramid itself has endured for more than 45 centuries. The knowledge that built it lasted for perhaps 3 or 4 generations at its peak level and then began to erode. The stone outlasted the knowledge by a factor of more than 10, and this is the deepest irony of the Great Pyramid. The builders created something that was designed to last forever, and it has. But the knowledge that created it, the capability that made it possible, was gone within a few lifetimes. Let that sink in. The stone endures, the knowledge does not. The product is permanent, the process is ephemeral, the pyramid stands, the builders are forgotten, not merely dead, which is the fate of all human beings, but forgotten in the specific sense that what they knew, how they did what they did, has been lost beyond recovery. We can measure their work to the millimeter. We can analyze their materials to the molecular level. We can model their logistics with computer simulations. But we cannot replicate their achievement, because the knowledge that would allow us to do so does not exist in any form that we can access. There is a particular poignancy in the fact that the most detailed surviving ancient account of the Great Pyramid's construction, the passage in Herodotus's histories, was written more than 2,000 years after the pyramid was built, and is acknowledged even by its author to be based on second-hand information. Herodotus visited Egypt in the 5th century before the Common Era, at a time when the pyramid was already more ancient to him than he is to us. The priests who served as his guides were themselves separated from the pyramid builders by a vast gulf of time and cultural change. The information they conveyed to Herodotus was a mixture of genuine tradition, educated speculation, and popular legend, filtered through centuries of retelling. It is, at best, a distant echo of the original knowledge. And yet Herodotus's account is the closest thing we have to a contemporary description of the construction process. All of our other sources are modern, working backward from the physical evidence to infer the methods used. The gap between the last person who actually knew how the Great Pyramid was built and the first modern person who tried to figure it out is measured in thousands of years. In that gap, the knowledge was lost, not gradually, not partially, but completely. When Champollion deciphered the hieroglyphs in 1822, he opened a door to Egyptian language and literature, but he did not open a door to Egyptian construction knowledge, because the Egyptians, as far as we know, never wrote down how they built the pyramids. The knowledge was too practical, too embedded in craft tradition, too much a matter of doing rather than describing. It was the kind of knowledge that lives in hands, not in texts, and hands do not survive. The concept of institutional knowledge is central to understanding what was lost. Institutional knowledge is the collective understanding that resides within an organization, not in any single individual, but in the interactions, procedures, standards, and shared assumptions that define how the organization operates. A modern construction company possesses institutional knowledge that is distinct from the personal knowledge of any of its employees. This institutional knowledge includes standard operating procedures, quality control protocols, supplier relationships, safety practices, and the accumulated experience of past projects. It is not written in any single document. It exists in the culture of the organization, in the way things are done, in the expectations and standards that every employee absorbs through the process of working within the system. The institution that built the Great Pyramid possessed institutional knowledge of extraordinary depth. It knew how to quarry stone of specific types and dimensions from specific locations. It knew how to transport that stone over long distances using boats, sledges, and possibly rollers. It knew how to prepare foundations and establish reference planes. It knew how to cut and fit blocks to precision tolerances. It knew how to manage a workforce of thousands, organizing them into teams, feeding them, housing them, treating their injuries, and maintaining morale across a project that lasted 2 decades. It knew how to maintain quality standards across millions of individual operations, and it knew how to solve problems as they arose, adapting its methods to the specific challenges of each stage of construction. All of this knowledge was maintained within the institution. When the institution flourished, when it had adequate resources, sufficient labor, and the ongoing demand for its services, the knowledge was maintained and refined. Each pyramid project added to the institutional knowledge. Each innovation was incorporated into the standard practice. Each solution to an unexpected problem expanded the repertoire of techniques available for future projects. But when the demand for pyramids declined, the institution that built them began to shrink. Fewer projects meant fewer workers. Fewer workers meant less opportunity for training. Less training meant the loss of the most refined skills, the ones that required the most practice to develop and maintain. The institution that had built the Great Pyramid did not disappear overnight. It contracted gradually, over generations, losing capability with each contraction. The pyramids of the 5th dynasty were smaller and less precise than the Great Pyramid. The pyramids of the 6th dynasty were smaller still. By the Middle Kingdom, the pyramid-building institution had been so diminished that the structures it produced bore only a superficial resemblance to the monuments of the Old Kingdom. The stones were smaller, the construction was less careful, the precision was a fraction of what it had been. The trajectory is a textbook case of institutional decay. An institution reaches a peak of capability, supported by sustained demand and adequate resources. The demand declines. The resources are redirected. The institution adapts by cutting costs, reducing training, accepting lower standards. Each adaptation is rational in the short term, but corrosive in the long term. The institution survives, but in a diminished form, and eventually it reaches a point where the gap between what it can do and what it once could do is so large that the connection between the two is barely recognizable. We see this pattern in our own time. Manufacturing industries that move their production overseas often find that when they try to bring production back, the institutional knowledge has been lost. The factories can be rebuilt, the machines can be purchased, the manuals can be recovered, but the accumulated know-how of the workforce, the subtle skills, and the tacit knowledge that made the operation run smoothly is gone. It was carried by people who retired or moved on. It was maintained by systems that were dismantled. It was embedded in a culture that no longer exists. And rebuilding it takes years, sometimes decades, and it is never quite the same. The ancient Egyptians experienced this on a civilizational scale. The institution that built the Great Pyramid was arguably the most capable construction organization in the history of the pre-industrial world, and it was lost, not through catastrophe, but through the gradual, ordinary process of institutional decline. The demand for pyramids decreased, the resources available for construction diminished, the workforce shrank, the training pipelines narrowed, the standards slipped, and within a few centuries, the knowledge that had made the Great Pyramid possible was a memory. Within a few more, it was not even that. The implications of this distinction extend far beyond ancient Egypt. Consider the knowledge that sustains our own civilization. How much of it is information, and how much of it is capability? The plans for a modern skyscraper are information. They can be stored, copied, and transmitted. But the ability to build a skyscraper is a capability. It requires not just plans, but skilled workers, specialized equipment, supply chains, quality control systems, regulatory frameworks, and institutional knowledge that exists within construction companies and engineering firms. Remove any of these elements, and the capability is diminished or destroyed, even if the information survives intact. Let that sink in. Our civilization, like every civilization before it, is built on capabilities that are more fragile than the structures they produce. The buildings will outlast the knowledge, just as the pyramid has outlasted the knowledge of its builders. And the moment we stop actively maintaining and transmitting the capabilities that sustain us, those capabilities will begin to erode, just as the pyramid building capability eroded after the age of Khufu. This is not science fiction. This is the documented reality of every complex skill set in human history. The knowledge of how to build medieval cathedrals was largely lost during the early modern period and had to be painstakingly reconstructed by preservation specialists in the 19th and 20th centuries. The knowledge of how to construct traditional Japanese wooden buildings using interlocking joints without nails is maintained today by a handful of master carpenters whose numbers are declining. The knowledge of how to produce certain traditional materials, from specific types of mortar to specific types of glass to specific types of steel, has been lost and partially recovered multiple times across the centuries. The Great Pyramid is the most dramatic example of this pattern because the gap between the documented capability and the recoverable knowledge is so vast. But it is not unique. It is simply the largest and oldest instance of a universal phenomenon. Knowledge is created by practice, it is maintained by transmission, and it is destroyed by neglect, not by burning, not by conquest, by neglect, by the quiet, unremarkable process of one generation failing to teach the next what it knows. There is a deeper philosophical dimension to this that the Great Pyramid forces us to confront. We tend to think of knowledge as cumulative. Each generation knows everything the previous generation knew, plus more. History is progress. The arrow of knowledge points forward. The Great Pyramid challenges this narrative. It demonstrates that knowledge can be lost, that the arrow can reverse, that a society can know things that its descendants cannot even comprehend. The builders of the Great Pyramid possessed capabilities that we, with all our modern technology, cannot fully explain. They did things that we cannot replicate. They achieved precision that we struggle to match. And they did all of this more than 4,500 years ago. This does not mean they were superior to us. It does not mean they had access to mysterious forces or forgotten technologies beyond our understanding. It means that they had developed, through generations of sustained practice and institutional investment, a specific set of capabilities that were optimized for a specific task. They were the best in the world at building pyramids, just as the makers of Damascus steel were the best in the world at forging swords, and the builders of the Antikythera mechanism were the best in the world at constructing gear-driven astronomical models. Each of these achievements represents a peak of capability that was reached through long effort and lost through disuse. The peaks are different. The pattern is the same. The teaching of Hardjidef, a wisdom text attributed to a prince of the 4th dynasty, the same dynasty that built the Great Pyramid, includes a passage that is often interpreted as a reflection on the permanence of written knowledge. The text advises its reader to make their house in the graveyard, meaning to invest in the construction of their tomb, because the houses of the living decay, while the houses of the dead endure. This passage reveals a cultural understanding of permanence that was rooted in material form. Stone and mortar endure. Flesh and breath do not. The Egyptians understood this acutely. Their entire funerary tradition was built on the principle that material preparations could ensure survival beyond physical death. But there is a bitter irony in this understanding. The Egyptians were right that stone endures. The pyramids and the tombs have survived. But they were wrong about what matters. The stone preserves the container, but not the contents. The tomb preserves the body, but not the person. The pyramid preserved the achievement, but not the knowledge. The material survives. The immaterial does not. And the immaterial, the knowledge, the skill, the understanding, the organizational wisdom, is the thing that mattered most. The pyramid is a product. The knowledge was the producer, and we have lost the producer while the product endures. This paradox is not lost on modern researchers. The Egyptologist Barry Kemp of the University of Cambridge, who has spent decades excavating the site of Amarna, has written eloquently about the difficulty of reconstructing ancient mentalities from material evidence. Kemp argues that the physical remains of an ancient civilization are, at best, a partial and distorted record of the society that produced them. The things that survive stone, metal, fired clay, are the durable minority. The things that perish, wood, textile, papyrus, food, human bodies, and above all, human knowledge, are the perishable majority. We study the minority and try to infer the majority. The inference is always incomplete. In the case of the Great Pyramid, the inference is particularly challenging because the achievement is so extreme. The precision of the construction, the scale of the logistics, the sophistication of the engineering, all push against the boundaries of what we believe was possible with the known ancient toolkit. And every time a new measurement reveals a new level of precision, every time a new technology reveals a new hidden feature, the boundaries are pushed further. The Great Pyramid does not become less mysterious as we learn more about it. It becomes more mysterious because each new discovery reveals another layer of knowledge that we cannot fully explain. Something is wrong with our assumptions about the permanence of knowledge. The Great Pyramid tells us so. Every lost craft tradition tells us so. Every skill that was once common and is now rare tells us so. Knowledge is not a thing that, once acquired, persists automatically. It is a process that must be actively maintained. And the moment we forget this, the moment we assume that what we know today will always be known, we begin the slow, quiet process of losing it. There is a moment, standing at the base of the Great Pyramid, when the scale of it overwhelms everything else. The mind cannot hold the entire structure at once. It can see the stones at eye level, each one taller than a person, each one weighing more than a car. It can follow the courses of stone upward, watching them diminish with distance until they blur against the sky. But it cannot grasp the whole. The pyramid is too large for human perception to encompass, and in that inability to grasp the whole lies a metaphor for the knowledge that built it. We can see parts of it, we can measure parts of it, but we cannot hold the whole of it in our understanding. The Great Pyramid is not the only ancient structure that exceeds our ability to explain it completely. The megalithic temples of Malta, dating to approximately 3600 before the Common Era, include structures that predate the pyramids by more than 1,000 years and that were built using limestone blocks weighing up to 20 metric tons. The methods by which these blocks were moved and placed on a small Mediterranean island with limited resources remain poorly understood. The precision stonework of Sacsayhuaman, near Cusco in Peru, features blocks weighing up to 125 metric tons, fitted together without mortar in irregular, interlocking shapes so precise that a knife blade cannot be inserted between them. The Inca possessed no written language and left no technical records. The knowledge of how they achieved this stonework was lost with the destruction of their civilization by the Spanish conquest. The Great Wall of China, the Roman aqueducts, the Cambodian temple complex of Angkor Wat all represent achievements that required knowledge systems of enormous depth and complexity, and in each case, significant aspects of the knowledge that produced them have been lost. The Roman aqueduct builders possessed a practical understanding of hydraulic engineering, gradient calculation, and water management that allowed them to deliver clean water across distances of more than 100 kilometers with a fall of less than 1 meter per kilometer. The specific techniques they used for surveying these gradients, for waterproofing the channels, and for managing the flow of water through cities with populations of hundreds of thousands are only partially understood today. The Inca stonework at Sacsayhuaman deserves a closer look because it presents a different but equally baffling example of precision stonework. The walls of Sacsayhuaman are constructed from enormous blocks of limestone and andesite, some weighing more than 100 metric tons, fitted together without mortar in irregular, polygonal shapes that interlock like the pieces of a three-dimensional jigsaw puzzle. The joints between the blocks are so precise that, as noted earlier, a blade cannot be inserted between them. This precision was achieved on blocks of irregular shape, not rectangular blocks, which means that each block had to be individually shaped to fit the blocks adjacent to it. There is no standard shape. Every block is unique. Every joint is unique. The fitting process required the stonemasons to work each block until it conformed precisely to the surfaces of its neighbors. How they did this is not known. The Inca had no written language and left no technical records. Spanish chronicles describe the construction process in general terms, mentioning the use of stone hammers, bronze tools, and the labor of large numbers of workers. But these descriptions do not explain the precision. They describe the tools but not the technique. They describe the labor but not the method. The knowledge of how to fit 100-ton irregular stone blocks together with zero-gap precision was held by the Inca stonemasons and was lost with the destruction of their society. The comparison with the Great Pyramid is instructive. Both represent peaks of precision stonework achieved by civilizations that possess tools and methods we cannot fully reconstruct. Both demonstrate capabilities that modern experiments have failed to replicate. Both were products of institutional knowledge systems that were destroyed when the societies that maintained them were disrupted, and both stand today as mute testimony to what has been lost. There is a broader philosophical point here that extends beyond any specific civilization or monument. Every complex skill that human beings develop is a response to a specific set of conditions. The skill is developed because it is needed, it is refined because there is demand for refinement, it is maintained because the conditions that created the demand persist. When those conditions change, the demand diminishes and the skill begins to decay. This is not a failure of will or intelligence. It is a structural feature of how knowledge works. Knowledge is ecologically dependent. It exists within an environment of need, practice, and support. Remove the environment, and the knowledge cannot survive. The Great Pyramid is the supreme example of this principle. It exists because a specific set of conditions, a powerful centralized state, a religious ideology that demanded monumental tomb construction, a productive agricultural economy that could support a large specialized workforce, and a centuries-long tradition of refined stoneworking converged for a brief period in human history. When those conditions changed, the capability that had produced the pyramid was no longer sustainable. The knowledge was not forgotten in the sense that someone decided to stop teaching it. It was forgotten in the sense that the conditions that had created and sustained it no longer existed. The pattern is consistent. Complex achievements require complex knowledge. Complex knowledge requires institutional support for its development and transmission. When the institutions fail, the knowledge is lost, and the loss is not reversible, because practical knowledge cannot be reconstructed from the products it created. You can analyze a Roman aqueduct in every detail and still not know how to build one, because the knowledge of building was not in the aqueduct, it was in the builders. There is a pause that comes when you truly absorb this. A philosophical pause that has nothing to do with ancient Egypt and everything to do with the present moment. We are the heirs of a knowledge tradition that stretches back thousands of years. Every skill we possess, every technology we command, every system of organization we rely upon was developed by human beings who lived before us and who transmitted their knowledge to us through an unbroken chain of teaching and learning. If that chain breaks, even partially, even for a single generation, the knowledge it carries is diminished, not destroyed perhaps, not completely lost, but diminished, and each diminishment makes the next one more likely. The Great Pyramid stands at the beginning of recorded history, a monument built at the dawn of the literate age. It was designed to endure forever, and it has. But the knowledge that built it, the finest achievement of the minds and hands that created it, was more perishable than the stone. It was more perishable because it was alive, because it existed in human minds and human institutions and human relationships, because it depended on being needed, on being practiced, on being valued enough to transmit. And when it was no longer needed, no longer practiced, no longer valued, it died, while the stone lived on. We build monuments to what we value. The Great Pyramid was a monument to the pharaoh's eternity, but it has become unintentionally a monument to something else. A monument to the fragility of knowledge, a monument to the impermanence of capability, a monument to the truth that the most extraordinary things human beings can do are also the most easily forgotten. There is a story, probably apocryphal, but revealing in its implications, about Napoleon Bonaparte's visit to the Great Pyramid during the French expedition to Egypt in 1798. According to the story, Napoleon entered the king's chamber alone and emerged sometime later, visibly shaken, refusing to speak about what he had experienced inside. On his deathbed, years later, he was asked about the incident and reportedly began to speak before stopping himself and saying that there was no point, that no one would believe him. The story is almost certainly a fabrication, embellished over generations of retelling, but it captures a genuine response that many people have when confronted with the interior of the Great Pyramid. The sense that the structure contains more than meets the eye, that the precision and the scale and the age of it combine to produce a feeling that exceeds rational explanation. This feeling is not supernatural. It is the natural human response to encountering evidence of a capability that one cannot comprehend. We understand intuitively that the Great Pyramid represents an extraordinary achievement. We understand that the people who built it knew things that we do not know. And we understand, at some level below conscious articulation, that the loss of that knowledge diminishes us. It diminishes us because it narrows our understanding of what human beings can do. It limits our conception of the possible, and it confronts us with the reality that knowledge, the most precious product of human civilization, is also the most perishable. The Great Pyramid will stand for millennia to come. Barring catastrophic seismic activity or deliberate destruction, it will outlast every building currently standing on Earth. It will outlast the skyscrapers and the bridges and the dams and the monuments of our own civilization. Long after the last steel beam has rusted and the last concrete wall has crumbled, the Great Pyramid will still be there, sitting on the Giza Plateau, its mass undeniable, its precision undiminished, its silence unbroken, and future generations, whatever form they take, will look at it and ask the same question we ask. How? How did they do this? And the pyramid will not answer, because the pyramid is stone, and stone remembers the shape it was given. It does not remember the hands that gave it. The Egyptian scribe who composed the text known as the Teaching of Kheti, or the Satire of the Trades, wrote that the scribe's profession was the only one that offered true permanence. All other crafts, the masons, the farmers, the soldiers, were subject to the body's decay. But the scribe's words, committed to papyrus, would endure. There is a deep irony in the fact that the scribe's words about permanence have survived, while the knowledge of the masons who built the pyramids has not. The scribes were right about their own permanence, but they were wrong about the masons' impermanence being a lesser thing. The masons' knowledge, the knowledge of how to cut and fit and raise and align millions of tons of stone with a precision that has endured for 45 centuries, was perhaps the most extraordinary intellectual achievement of the ancient world, and it was lost while the scribe's reflections on its insignificance survived. There is a passage inside the Great Pyramid that most visitors never see. It runs upward through the heart of the structure at a precise angle of 26 degrees and 31 minutes, lined with polished limestone of extraordinary smoothness. The walls are close, the ceiling is low, the air is still and warm, carrying the faint mineral smell of stone that has been sealed from the world for millennia. This passage is called the Ascending Passage, and it leads, eventually, to the Grand Gallery and beyond it to the King's Chamber, where a granite sarcophagus sits empty in the silence, robbed of its contents long before the first modern explorer entered the room. Walking through this passage, if one has the privilege of doing so, when the crowds are absent and the lights are dim, is an experience that changes the quality of one's thinking. The precision of the stone is palpable. You can run your hand along the wall and feel the flatness of a surface that has not changed in 4,500 years. You can see, where the light catches the stone at a shallow angle, the faint traces of the tools that shaped it, the marks of a civilization reaching beyond itself. And you can feel, in the tightness of the space and the weight of the stone above and around you, the presence of knowledge, not mystical knowledge, not supernatural knowledge, human knowledge. The hard-won, painstakingly developed, generation upon generation accumulated knowledge of people who understood stone the way a musician understands sound. People who could make stone do things that we cannot make it do because we have lost what they knew. The Great Pyramid is a time capsule, but not in the way that phrase is usually meant. It does not contain messages from the past. It does not preserve artifacts or records for future generations to discover. It preserves something more fundamental and more haunting. It preserves the evidence of a capability that no longer exists. Every precisely fitted joint, every perfectly level course, every optically flat surface is a data point in a dataset that describes a knowledge system we cannot reconstruct. The pyramid is not a message. It is a demonstration of what human beings could once do, and a reminder of how thoroughly that capacity can be erased. The stonemasons who dressed the casing blocks of the Great Pyramid spent their lives perfecting a skill that would not be needed by their grandchildren. The surveyors who aligned the base to true north possessed a methodology that would be obsolete within a few generations. The foreman who managed the placement of blocks with the coordination of a military operation developed logistical skills that would never again be applied at the same scale. Each of these individuals carried a piece of the knowledge. Each of them taught some of what they knew to younger workers. But the whole of the knowledge, the complete system that made the Great Pyramid possible, was too large, too complex, too dependent on institutional support and sustained demand to survive the end of the pyramid building era. Every civilization believes that its knowledge is secure. Every generation assumes that what it knows will be known by those who come after. The builders of the Great Pyramid certainly believed this. They built for eternity. They carved their pharaoh's name in stone. They created a structure designed to outlast time itself. And they succeeded. The structure endures. But the knowledge that created it, the real treasure, the irreplaceable achievement, is gone. The stone remembers nothing. It holds its shape. It keeps its alignment. It preserves the evidence of what was done to it. But it cannot tell us how. It cannot teach us the skills of the people who shaped it. It cannot transmit the judgments, the calculations, the physical intuitions of craftsmen who died more than 40 centuries ago. We live in an age that records everything. We photograph our meals and archive our conversations and store our data in clouds that are maintained by machines that are monitored by other machines. We assume that nothing can be lost because everything is recorded. But the Great Pyramid was also a record. Every block is a record of a cutting technique. Every joint is a record of a fitting method. Every angle is a record of a measurement process. And these records, carved in the most durable material available, have been studied for 200 years by the most capable researchers in the world, and they still have not yielded the full story of how the pyramid was built. Recording is not understanding. Preservation is not transmission. Data is not knowledge. The Great Pyramid preserves the data of its construction with perfect fidelity. The angles are still exact. The surfaces are still flat. The alignments are still true. But the knowledge that produced this data, the living, breathing, practiced knowledge of human beings who understood what they were doing, is beyond recovery. It exists now only in the negative space, in the gap between what we can measure and what we can explain, in the silence where an answer should be. There is one more thing to say about the lost knowledge of the Great Pyramid, and it may be the most important thing of all. The knowledge was not one thing. It was many things. It was the knowledge of the astronomers who determined true north. It was the knowledge of the surveyors who laid out the base. It was the knowledge of the quarrymen who extracted the stone. It was the knowledge of the transport crews who moved it. It was the knowledge of the masons who shaped it. It was the knowledge of the engineers who designed the internal structure. It was the knowledge of the managers who coordinated the entire operation. It was the knowledge of the laborers who did the heavy lifting literally, day after day, year after year, for 2 decades. Each of these groups possessed specialized knowledge. Each group's knowledge was necessary, but not sufficient for the whole. The pyramid could not have been built by astronomers alone, or engineers alone, or masons alone. It required all of them, working together, within a system that integrated their specialized knowledge into a unified operation. This is the most fragile form of knowledge, not individual expertise, which can be maintained by a single dedicated practitioner, but systemic expertise. The knowledge of how to combine specialized skills into a coordinated whole. The knowledge that exists not in any individual, but in the relationships between individuals, in the communication channels, in the coordination protocols, in the shared understanding that allows a complex operation to function smoothly. This systemic knowledge is the first to be lost when the system is disrupted, because it depends on the system itself. You can preserve the knowledge of an individual craftsman by maintaining a single apprenticeship relationship, but you cannot preserve the knowledge of a system except by maintaining the system. The Great Pyramid was the product of a system. The system is gone, the pyramid remains, and in the space between the enduring stone and the vanished system lies the full measure of what we have lost. Not a technique, not a tool, not a secret, a way of working together, a way of combining human capabilities into something greater than any individual could achieve, a way of making the impossible possible through the organized application of ordinary human skills. That is what was lost, and that is what the Great Pyramid mourns in its silence. The sun sets over Giza, as it has set every evening for more than 4,500 years. The shadow of the Great Pyramid stretches eastward across the plateau, reaching toward the Nile, reaching toward the city of Cairo, reaching toward a world that the builders could not have imagined and that cannot imagine them. The pyramid will stand tomorrow as it stood yesterday. Its precision will not diminish, its alignment will not drift. Its stones will hold their places as they have held them since a civilization at the peak of its knowledge set them there, and then, slowly, quietly, across the centuries, forgot how. The wind blows across the Giza plateau, the tourists leave, the guards settle into their posts, and in the growing darkness, the Great Pyramid stands alone with its knowledge, a knowledge written in stone and readable by no one, a testament to the most extraordinary thing human beings can build, and the most ordinary way they can lose it. Not through fire, not through war, through the gentle, relentless passage of time, which spares the stone and takes the minds that shaped it, which preserves the monument and erases the meaning, which leaves us standing at the base of something magnificent, looking up, unable to explain what we see. The stones hold their silence. They have held it for 45 centuries. They will hold it for 45 more. And somewhere in that silence, in the space between the blocks where the joints are too tight for paper, in the angles that are too precise for explanation, in the surfaces that are too flat for the tools we think were used, the lost knowledge waits, patient, perfect, gone.